slide'ı göremiyorum ama.
Gelmiyor mu? Slide'ı başka göremeyen var mı?
Ben görüyorum hocam.
Okey. Yani şu menülerde minimize etmiş falan olabilir misin bilmiyorum Hamdi. Anyway, so in the last lecture we talk about different winding configurations for permanent magnet machines. I mean, the first one is like we have a full pitch winding, so from here to that side. Then also our magnets has 180 degrees electrical pitch. So basically we have a full pitch winding. So what is happening is, they have the maximum value here, and as the rotor rotates, the flux increases linearly, reaches to a maximum value, then decreases linearly as well. So that is the kind of voltage waveform that we will see with that kind of configuration. And actually the induced voltage, induced back EMF voltage, is the derivative of that flux. So when you take the derivative, so basically whenever you have constant slope, it means you have a constant induced voltage. Then when it is reducing, then it reduces, so you get a kind of square waveform. So then we looked at the fractional pitch coil. So basically what I did here is just use a shorter pitch coil. So instead of spanning the all 180 degrees electrical, now it is shorter, or it can be longer. It is the same logic. So now here, for example, you have a maximum value, so all the coils are linked by the south pole, and if you rotate the rotor clockwise, so the coils will still see just the south pole magnet, so the flux linkage will increase, then stay constant for some time until you have the north pole coming into the coil. So from now on, then you will have a reduction. So basically that will that is the version that we have with the full pitch coil. So now we have a short pitch coil, so now it is like a trapezoidal shape, like in this case, and therefore since we are using a shorter pitch, now we have the maximum flux linkages reduced from that point to below that point. Anyway, so if you take the again derivative of that waveform, basically you will have a constant voltage, and whenever flux is constant, the absolute value does have no meaning. What we are interested in is the derivative of the flux. So since the derivative of the flux is 0, we see 0 voltage here, and then it goes negative. So it is like a square wave, but with some 0 regions in between. Okay. Then we can do basically the disadvantage of the previous one. If I just open it, let me try to take it from here. Okay, tabletten çiziyorum da. So what's going to happen is, yes, you can have some flux are traveling through here, so that will be our main leakage flux, but we will also have some of the flux just rotating, just closing their circuits through those adjacent points, and those are not linking the coils. So this is called the leakage flux. So one way to reduce the leakage is just to increase the distance between the permanent magnets, so it will be easier for flux to travel through the air gap compared to just pass through the air gap. So basically that is the main the main aim of using a shorter pitch coils, like in this case. So for example here, now the magnets are not touching each other, so it is easier for flux to just go through the air gap than go to the south pole through here, instead of going all that air gap distance between two magnets. So basically, you reduce the magnet mass, so you reduce the cost, but the flux linkage in the coil is not decreased that much. So there's an optimum point, which is one of the objectives of optimizations in electrical machines. So anyway, if you do that one, basically it is the same thing. So now we have a full pitch coil and a short pitch magnet. So basically, even if you have a shorter pitch magnet, now all the flux is linking the coil, and that maximum flux linkage is not going to change until you have the north pole get into the coil. So basically it is similar to what we have. It is like that. So it's similar to what we have with the short pitch. So it is a square waveform with zero regions. Okay. So then, var mı buraya kadar sorusu olan arkadaşlar? Okay. So then what we are going to do is we are going to combine multiple coils. So here again, it's kind of an unconventional machine, but never mind. So here again we have a 4-pole machine, so north south, and we have 15 slots. Okay, we have 15 slots, and let's say the coil span is like 4 in this case, so 4 here, 4 here. So actually, you can calculate the electrical angle between each slot, and I think it was, if I remember correct, so the pitch of those coils is 192 degrees, so it is slightly larger than 180 degrees. But anyway, once you have that connection, okay, once you have that connection, so what you have is, it is a short pitch coil or a long pitch coil, it doesn't really matter in terms of the flux linkage. So you have that kind of trapezoidal waveform, and that is the back EMF voltage in one coil. So that is the back EMF voltage in one coil. So what we are going to do is, we have basically 5 of those coils. So by 5, so it is, let's say, the first coil, the second coil, third coil, fourth coil, and fifth coil. So basically, again, it is not really conventional design, but anyways. So you have basically 192 degrees shifted, and actually if you just plot those things, you have either, the first one is minus 12, the other one is 24, the other one is minus 24, the other one is plus 12 degrees. So you have not exactly the same voltage, but it's the same waveform, but shifted with respect to your pitching factor. So basically, when you just add them together, you can just combine that one, that one, that one. What you have is that kind of voltage. So that is very similar to what we are doing in the early weeks. So basically, we can use many coils. Furkan, soru mu var? Açık mı mikrofon?
Hocam düştü de, pardon.
Okay, sorun değil. Anyway, so we just add many coils in series. So by that way, you can get a more sinusoidal distribution. And again, this is a rough approximation, because in that one, we assume the flux linkages have really sharp edges, and the induced voltage has really sharp edges. But in reality, there will be some leakage flux, so this will be kind of round. Therefore, the induced voltage will have some kind of round shapes here. And as a result, basically, the induced voltage will be much sinusoid shape compared to that one. Okay, any problems? So can we connect those windings in parallel? But what will happen if I just connect the first one and the second one in parallel?
Faz farkı olduğu için incirculating current'ları oluşacak.
Yes, I mean, if you just connect like 2 coils, let's say this one will be EA and the second one will be EB, like that. So I'm just connecting this one. So yes, for maybe that instant, it will not be a problem. So both of the voltages are equal. But for example, at that instant, the other one will be 0. And then that will be, trying to get some voltage. And basically, if this is your phase connection, let's say phase A, instead of that, currents are going to your load, or instead of your supplying power, you will have some coils, some currents between coils. So these are called circulating currents. These are called circulating currents. And it is not allowed to have parallels between those coils if you have even a slight voltage difference between the coils. I mean, in practical cases, even if you want to have the ideal voltage, there can be some non-idealities in the manufacturing. The coil positions can be shifted, the air gap can be slightly longer or shorter, the magnets at that coil can be slightly stronger than the other one. So paralleling coils can be dangerous in sometimes. So in general, we try to avoid the parallels, but in series, it doesn't make any difference, apart from the slight reduction due to the winding factor. So at least you are not generating any excessive heat. Okay. Cool. So, based on those things, I just want to, we will just cover those topics in detail in the following weeks, the types of permanent magnet machines, but just to, have a short intro. So basically we can have, you hear those things, either PMSM or BLDC. So PMSM is short for permanent magnet synchronous motor or synchronous machine. So they are mainly used like as in large servo motors, like accurate position control, speed controls, that kind of things, PMSM machines. So basically then we can have the brushless DC motors, or in short BLDC motors, and they are usually preferred in low cost small motors. And why one of them is called the BLDC, I mean, even if it is called DC BLDC, so you can see basically it has 3 terminals. It is not a DC motor, like as in conventional DC motors with the brushes and carbons. But it is a AC motor. So the difference actually comes from the figures that I just showed. It is coming from the back EMF. So basically with the PMSM, basically the back EMF is kind of sinusoidal. Okay, so that means you have enough number of slots and you adjusted either the permanent magnet shape, or you adjusted the coils connection, so you connected, I don't know, several coils in series, whatever you did. So your aim is to obtain a sinusoidal back EMF. So if you have a sinusoidal back EMF like that, basically you can drive that machine like as a with a AC voltage source. So basically all your parameters are sinusoid, and you can apply vector control like in the induction motor. You can have sinusoidal back EMF, and you can have precise motion control. So these are that higher performance over BLDCs. Okay, BLDCs on the other side, just to go back, so they are kind of small motors. And if you have a small motor, and actually the cost will be small, and apart from the cost, basically you will have a less circumference to open the slot. So maybe it will not be possible to open 30-40 slots in that kind of small machine. So basically you are trying to simplify your manufacturing. So you want to open as a small number as stator slots, and therefore you have maybe 1 or 2 coils per phase. So because of that, so you will not have the option, to connect those things like in series to obtain a sinusoidal waveform, but most of the time you will have that kind of a waveform. And they are called BLDCs because if you look at the back EMF, it is like a trapezoidal back EMF. Okay, so again, it doesn't mean like every small motor is BLDC and every large motor is PMSM. So usually it is specified in the datasheet, but if you have any doubts, just connect the oscilloscope, rotate the motor that like at no load with your hands, so just to see the waveform of the induced EMF voltage. So anyway, if you have that kind of system, so usually, you know, those BLDC motors are driven again by an inverter, but they are not driven by high frequency sinusoidal PWM. Instead of, they are driven by a current waveform. Either they are called like the 6-step driving, so you are just opening one of the phases and the other phase, so you are circulating the current, so the current is like that waveform. Okay, so again, it is okay for small power and low cost applications, but it is more difficult to have sensitive, you know, position control with that kind of topologies. Any questions?
Hocam, bu high power application'larında nasıl sıkıntılar ortaya çıkıyor BLDC'ler için?
Yok, şeyler ortaya çıkmıyor. Yani şöyle, hani high power'da gene şey yapacağım, hani büyük bir motorum var, 10 kW'lık var. Yine BLDC yapacağım dersen işte bu sefer şeyler falan, yani şu akım ve BKMF şeyinden de tahmin edebileceğin gibi hani harmonik sorunları genelde sıkıntı çıkarıyor. Yani harmonik ne demek? İşte sen kare dalga veriyorsun. İşte tamam, onun fundamental component'ı senin torkunu yaratıyor. Ama onun daha üstündekiler işte bir hani torkta ripple yaratıp hızda böyle oynamalara sebep olabilir. İkincisi ve daha önemlisi işte bu sefer o, yani normal senkronize göre daha hızlı dönen bir harmonikler olacağı için işte onlar loss'lara, işte core loss'lara da neden olabilir. Permanent magnetlerin üstünde eddy akımları da endükleyebilir. Hani bir de şey de çok mantıklı olmuyor açıkçası. Hani büyük yarıçapa çıkıp böyle 6 tane slot yapıp işte oralara koca koca coil'leri böyle büyük tek slot halinde koyduğun zaman, hani şeyi büyüttüğün zaman, copper array'i büyüttüğün zaman bu sefer o en ortadaki coil dışarıya ısıyı kolayca veremiyor. Yani sen gene işte bu kare küpler oranı, hani şeyi çok arttırdığın zaman diameter'ı, şeyleri ufak parçalara bölmek, slotlara, coil'leri ufak parçalara bölmek termal açıdan da işte harmonikler veya diğer o etkiler açısından da daha önemli oluyor. İşte onun yolu da daha fazla slot açmak. Lan zaten daha fazla slot açtıysam niye onu BLDC yapayım diyorsun. Bu sefer işte şey bağlayayım, birbirinden kayıp bağlayayım. En azından sinusoidal back şeyim olsun istiyorum diyorsun. Ama işte atıyorum, mesela güç elektroniği tarafındaki kayıplar senin için hani önemlidir. Sonuçta PMSM'leri şeyle sürüyorsun, işte space vector ya da sinusoidal PWM'le. Sonuçta neyse anahtarlama frekansın, o kadar açılıp kapanıyor. Hani switching loss'lar oluyor ama mesela buradaki gibi böyle 6 step bir şeyle sürdüğün zaman hani şeylerin, anahtarların bir burada açılıyor, bir burada açılıyor, işte öbür faz burada açılıyor, burada açılıyor. Sonuçta 360 derecede 6 kere açı oluyorlar. Hani o açıdan da switching loss'ları çok daha düşük oluyor veya şöyle söyleyeyim, çok daha dandik anahtarlarla hani termal açıdan sorun yaşamadan da yapabiliyorsun. Okay. Var mı başka soru Gökhan veya başkası?
Yok hocam.
Okay. So, I mean, in the early weeks we talked about the D and Q axis as well. So if you remember, your first simulation was also on that topic. Again, we will investigate like the different types of permanent magnets in the following weeks. But you know, just to remind, what is SMPS or SMPMSM? What is it short for? Any idea?
Surface mount permanent magnet synchronous machine.
Yes, it is for, you know, surface mount permanent magnet synchronous machine. So that means you have the rotor surface and you are not doing any machining to the rotor surface, but you are just placing your magnets on top of that one. So basically you have that waveform. So the gray bits are your iron part, yellow is the permanent magnet. So this is your stator, this is your rotor. Sorry, this is your rotor, this is your stator. And as you can imagine, again, you know, the main magnetization axis is the D axis and Q axis is 90 degrees apart from that one. So this is my Q axis. So basically the blue lines here just shows the d-axis flux lines, or LD or RD, and that one represents the q-axis flux, and this is the LQ or RQ. So which one is higher, LD or LQ?
LD.
Bakalım, bir saniye şey yapıyorum.
Surface mount olunca eşit olmuyor mu?
Evet.
Bir saniye abi. Uyuyanları uyandıralım.
Bunu surface mount için diyoruz değil mi?
Surface mount için.
Yani bu geometri için eşit gibi görünüyor.
Mahmut Enes Puya dersi dinlemiyor herhalde, onlar gitmiş. Anyway. Puya da yaptı. Şunu yapınca geçen tıkanmıştı ama tekrar şansımı deniyorum. Neyse. Okay, so actually for this machine topology, okay, since you know what was the relative permeability of a permanent magnet?
Bir.
Yes, I mean, bire yakın. I mean, yes, you can argue it is slightly less than the reluctance is less than the air, but again that part is not that significant, so the permeability of the magnets are really similar to what we have for the air. So for flux it doesn't really make any difference either to go in that direction or in that direction. Okay, so in this case basically, you know, again I'm ignoring 1.05 of relative permeability of permanent magnets. You can assume them to have like relative permeability of 1. If you have that one, so then that means you have LD is equal to LQ for surface mount permanent magnet machines. What is the implication of that one?
Reluctance torque elde edemiyoruz demek aslında.
Evet, yani hani ilk şeyde de hani ilk haftalarda çözdüğümüz o sorularda da bahsetmiştik. Hani senkron makinalarda aslında iki tane torque komponenti var. Bir synchronous torque, bir de işte reluctance torque diye. Hani senkron torque dediğimiz tamamen sizin manyetik alanla akım arasındaki ilişkiden geliyor ve işte o load angle delta açısıyla orantılı. İşte diğeri de reluctance torque. O da tam tersine böyle şey olmasa bile, yani manyetik alan yaratmasanız bile aslında minimum reluctance pozisyonuna gitmeye çalışıyor. O da iki delta ile orantılıydı, hatırlarsınız salient pole synchronous motorlarda. Hani surface mount motorlar o açıdan cylindrical rotor synchronous machine kategorisinde ve işte reluctance torque yaratılmadığı için hani düzgün tasarlanan bir salient pole makineye göre torque density'leri birazcık daha düşüktür. Okay. What is IPM?
Interior permanent magnets.
Yes, I mean it is different from the surface mount permanent magnet. So here you don't just, you know, attach the magnets onto the surface of the rotor, but instead you are you are opening some slots in the rotor for the permanent magnets, and then you are using that slots to put the magnets in it. So basically, again, there are like many different types, but the usual shape is something like that. So one of the advantages is mechanical, because if you have a surface mount machine, and especially if it is a high speed machine, as it rotates, it creates lots of centrifugal force, and it just tries to come off from the rotor surface. But in the interior permanent magnets, you are putting it instead of some inside of some rotor steel. So even if they are trying to go away from the origin, they are held by that iron enclosure, so they are more suitable for high speed, robust applications and that kind of stuff. And again, basically you can just put the magnets and cover all that gap with the epoxy, and the magnets will be protected well against the corrosion, if you remember the surface coating options. So here, they are in a more protected environment. Anyway, so let's do the same question again. So which one is higher, LD, LQ, or they are equal? Hop. Pol gitti ya, göremedim. Ben tam şeyi üstüme aldım. Burada da mı göremiyoruz ya? Neyse, sonuçlarınızı göremedim. Okay, so basically what is happening here? What is happening here is, let's see, I will try to plot it. So for d-axis, we have the d-axis here, and if you are a flux, so now that yellow area, that permanent magnet area, is like an air for you. So you are passing from one air region, and then you are passing through another air region, okay, and then you are coming back another air region and another air region. Of course, the dimensions can be different, but basically in this case, in the d-axis, you have to pass through 4 air regions. I'm counting the permanent magnets as air, because again the permanent magnet relative permeability is close to 1. So basically in this case, RD is large, okay, the reluctance is large. However, if you look at the d-axis, I'm getting through here, I'm passing through one air gap and just traveling through the core, and I am just passing another air gap, then all the way back. So basically I don't cross those magnet thickness, instead I just traveled between the gap between the magnets. So therefore here I am passing just 2 air gaps, so here RQ is basically lower. So again, I know inductance is equal to N square over R, and a high reluctance means a low inductance. So basically what we will have is, I will have a lower reluctance in the Q axis, which means a higher inductance for the Q axis, and I will have a smaller inductance for IPM machines. And again, if you use it properly, if you designed your machine properly, that means on top of your synchronous torque, you can also generate a reluctance torque. So for example, even if you remove all the magnets in that motor, so remove the yellow bits, and if you apply a correct voltage waveform, current waveform, you will be able to rotate that machine like as a variable reluctance motor. Okay, so that means that reluctance torque can be added on top of the synchronous torque. So these are mainly preferred in where weight or torque density is important, like automotive applications. Most of the electric cars are using that kind of IPM motor structure, or aerospace applications. However, if you just don't design it properly, so that means you can generate some positive torque from the synchronous part, but you can generate some negative torque from the reluctance torque. So instead of adding up to your overall core, so it will behave like a brake. so it can make your performance even worse. Okay, any questions? We will see detailed things for that machines. Okay, if you don't have any questions, let's give a 5-minute break. So that is all for permanent magnets. So I would like to continue with the basic machine designs in the next lecture.